Thank you everybody for being here. This is the 2025 edition of the SISSA Women in Mathematics. I am Anna, I'm a PhD student here at SISSA, and I will chair this edition together with Isabella, which is another PhD student here. So I would like to welcome the speakers and guests of today's edition, Annamaria Ortu, Veronica Felli and Roberta Ghezzi. And we can start with the institutional greetings by the area coordinator, Professor Antonio Verario, and by Professor Domenica Bueti, who is the director of the CUG, Comitato Unico di Garanzia. So,
okay. All right, so good afternoon, everyone. I think I can just stay here. So I'm very glad to open this event. So this is it's become a tradition for our community to host this day, which will take some time to celebrate and to think about the role of women in mathematics. The event usually takes place around the birthday of Maria Mizzacani, who was the first only woman together. It's made up of 2017, just 68. And of course, like it's how to say, this was said, but Mizzacani was influential, continues to inspire. Also, today, this has been possible through the organizational efforts of Anna Ivanis and Isabella Mela, respectively the president and the vice president of SISSA signed to the chapter. So first of all, I need to thank them. I also want to thank Gianluigi, also not here, because he is the one who started this initiative some years ago, and even today, and I think he has played a meaningful role. We need to thank Sani for the support for this initiative, and the Department of Eccellenza of the Mathematics area as well, because they are supporting with their resources. So what's going to happen today? So I think it will be both scientific and reflective, as I understand correctly. So there will be some scientific talks. We'll hear from former SISSA alumni about their that are now science researchers, and we'll take some time to think, reflect, through, I think, an engaging game, right, that was thought as a stimulating. I hope this will be stimulating and it will feel meaningful for all of us, all stages of our careers. Before we begin, I'll pass the floor to she's the president of the movement here at SISSA.
Thank you. Thanks. It's very nice to be here with you, and I really would like to express really my gratitude also for letting me do this, let's say, guidance and welcoming. So as a chair of the Comitato Unico di Garanzia, so this well-being and equal opportunities committee, one of the tasks that I have is to collect data. And some of those data that concerns the gender composition of the school, right? And those numbers are actually not super reassuring since we are a STEM, let's say, institution. So only 30% of the researchers at SISSA, so researchers, I mean, from PhD students to full professor, only 30% are women. And of course, this percentage drops, as you would expect, below 20% when we talk about tenure position, right? And only 13% of the full professors are women. And of course, mathematics is also an area that SISSA has big areas in science, mathematics, and physics. And of course, physics and mathematics suffer more of this lack of gender balance, and this happens also, unfortunately, not just at the student level, but also at the application level. So there are only really 10% of candidates in mathematics are. So of course you understand that the importance, of course, to make concrete actions. This is one of the role that the PUG has at the school, so to try to suggest some actions that we could take. Of course, these are very important, to support the presence, to encourage the presence of women in academic roles and leading positions, also support the women in balancing the working and private life, but also, I would say, events like this are really very important to provide the young generations also with examples, having role models, ensure that actually we can do great research, we can be academics, so we can climb the stairs of the academic life. So thank you for organizing this and for being here, and enjoy really the science. That's the most important thing. Thank you.
Okay, so thank you, Professor Verario and Professor Gueti for your greeting. And so I guess we can start. Just a very quick announcement, especially to the online people. We've been notified that there can be interruptions in the internet connection till 3 p.m. So just to let you know that if the Zoom connection is down, it's because of this. Let's hope not, but yeah, there is the possibility. So, okay, so I think Professor Gueti and Professor Verario already gave a good introduction to this day, but I would like to restart, and I would like to say that we are here today to celebrate, of course, women in mathematics, as the name suggests, and to discuss why we are underrepresented, especially in our STEM field and in mathematics. Why April 14? Well, as Professor Rani said, May 12 is the birthday of the first women that won the Fields Medal, Maria Mirtakani. Actually, why April 14? The reason is that I and Isabella would not be in Trieste in May because we hopefully will be in the Netherlands for internships. So that's the reason why we anticipated a bit. So the only two women that won the fifth medal were Maria Mirtakani in 2014 and very recently Marina Desowska. So we have just two women over 64 winners in total. So you understand that this percentage is very, very low. So we are here also to discuss why this is low. Today's speakers, as we said before, are Professor Roberta Ghezzi from University of Roma Tor Vergata, Professor Veronica Felli from University of Milano Bicocca, and Dr. Annamaria Ortu from University of Gothenburg in Sweden. I here reported all the PhD dates because it's interesting to see that we have this year 3 different generations. So it's beautiful that you can somehow bring your experience, which is different, of course. Okay, so today's schedule is this one. So we start now with the panel discussion. Isabella will start with the panel, and then we will have the coffee break that will be at the ground floor. And then starting from 4 p.m., the scientific seminars by the speakers. Okay, so let's start now with the panel discussion, and I leave the word to Isabella.
Okay, hi everyone. Thanks, Anna, for the introduction of the event. We hope it will be interesting for you. Our idea is to actually go have an excursus through the stages of the academic career that every academic has gone through. Especially we will focus on some data on the gender gap in the various stages of the process. And we will try to understand together the meaning behind those data and maybe enrich also them with some personal experience from the speakers and some insights in personal academic paths. So then we will have an open discussion about the data that we will show, and going on, we hope to have a clear or maybe an interesting picture of what is going on, not only based on percentage, but also based on some personal experience of the job. So first of all, we would like to start with an icebreaker question for the speakers. We thought it would be interesting to bring some names on the table because as also Professor Antonio and anticipated, the role models are very important, and we feel that when we think about a mathematician, we always think about maybe a male professor who is doing some research on strange topics that do not belong to the common world. And so we would like to give also different opinions on that and maybe perspective to understand that maybe kids of a younger age that are deciding whether or not to pursue such career do not have to be discouraged if they do not feel that they could fit in those kind of stereotypes. So maybe some people have done something to change this idea, and so it is great that we mention them if you have someone in mind. So there are some names that come into your mind when I say that. Please go on and share with us if you, whoever wants to start. Please.
Okay, maybe I start. So yes, I would like to make the name of a present mathematician. It was particularly female mathematician was particularly inspiring for me. I would definitely mention Susanna Terracini, who was my mentor in the postdoc, and she was the first woman having for me this, let's say, mentoring, supervising role, because both supervisors of undergraduate thesis and doctoral thesis were men. So she was the first woman I met in this context. And she was inspiring for me, first of all, because she's an outstanding mathematician, but also for the energy, the passion that she puts in everything she does. So I think she had an important role also in my career choices. Thank you.
And I would like to mention first Maria Colombo, who is a well-established mathematician, analyst, and she recently won many prestigious prizes. And but the reason why I personally find her inspiring is, she is an expert in mathematical analysis, and I try to do research in mathematical analysis. She is a former student of Luigi Ambrosio, and I had the opportunity to work with him for a year, postdoc fellowship some years ago, and also I was personally very I was struck by the fact that she is a mother of 4 children. And so to me, she was really, she is, and lastly, she's a present mathematician. She's, I think, 6 years younger than me. So she I kind of feel her quite next to me for some reasons. And this is inspiring for me to see that there is an example of a person which is real, which is not I've never met her personally, but I could. I think I could on some occasions, scientific occasions. So she exists. She's next to me, and she is excellent not only as a scientific researcher, also as a scientific trainer of people. She trains people. She guides her. She's the head of her scientific group, and not let's say not forgetting, she is also a mother. And then while you were talking, I was thinking about other examples, which well, this may be out of topic now, but I want to say that when I was a PhD student, we were 4 women, and the 4 of us are now professors, 4 of them, and not all the men that were our colleagues. Many of them, I don't know the percentage, I didn't compute it, but some of them pursue different careers. So I would say, just as encouraging young women and PhD students, that probably if you are a PhD student, a female PhD student, you will end up being well, let's say based on my personal experience, you will end up being an academic. Whereas if you're a male one, you may not. Not false. I have someone who can testify for me here.
Yeah, I believe it's my turn. So I don't know if this works. Yes. Yeah, this is a tough question. I think if I have to name a woman mathematician who is very inspiring for me, I would name Frances Kirwan. She is, of course, she's just retired, so she is many generations before me. But she's kind of in my field, and I have met her a few times in conferences, and what she is extraordinary, and so I usually believe that role models should sort of be more like people that we can sort of aspire of becoming. But she's very modest and also very open to discuss with young people. She has mentored many students during the years. She has been in panels and committees. She's been very active towards inclusion of women in academia, and so she and everything with a very modest attitude and very nice person, and so I think it's my idea of successful. Yeah.
Well, perfect. Thank you very much for the very interesting and inspiring answers. Now that the ice should be break, we go on and we try to start from the ground stage of education, so from pre-university education. And when we try to compile those slides, we ask ourselves, okay, in which ways do female and male actually, if we're on a ground level, depending on their attitudes toward mathematics? Are there any differences? Are there any differences that could be measured in a statistic way? And we find some reports from an assessment made by Program for International Student Assessment, and they are kind of research that are done periodically, and in particular we found the one of 2015, which was particularly interesting for the mathematical attitude of kids. They are researchers. They are researches for 15-year-old people. So they are doing tests to see whether or not in various countries, the education is successful, especially in mathematical fields. So problem solving and how actually the kids are stimulated and how do they respond. We were curious not only about the statistics, but also about the general belief around those statistics. So what people think about actually the potential hidden in little girls and little boys, whether we think that they are actually different or not. So here we propose you a quiz, and for that you should be able to scan the QR code, and there will be a question, and the question will be, which are the main differences in 15 years old attitudes toward mathematics? You can do also. Okay.
Guys can also
Think about that.
Yeah,
if you want.
you can comment the noise.
Yes. We have put here 4 options for you. So the first one is there are no measurable differences in mathematical aptitudes between boys and girls. The second one is the girls are more confident in math but perform worse in all types of problem solving. The third is the reverse one, so boys are more confident but perform in a worse way. And then the fourth is girls outperform boys in collaborative problem solving, while boys outperform girls in individual problem solving. So when you're done, you can also raise your hand. So we will have statistics on when to proceed.
Define measurable.
Measurable through statistics, through tests. Like this assessment, they will take kids and maybe make them perform some kind of problem solving task and then give a point.
I guess they like kids some tests, individual or collaborative, and then just measure
the ability in different countries actually. So it's all over the world with different economies and cultures.
So what should we say? The true or false?
Yeah, which one is true?
Only one is true.
Only
Sorry,
one is true. Only one is true. Yeah.
if you have some feeling.
Yeah, you can please comment before we show the answers. So if you want.
3 looks true.
To me as well. Yes, I would
But also 4, I think. Also 4. Maybe look true.
So yeah, we voted. Everything good? Okay. That shouldn't be it. Okay. So the majority voted. There are no measurable differences in mathematical aptitudes. Okay. And then there is the second one, which is actually the third. Boys are more confident in math, but of course. So the right answer is actually the fourth.
No.
Okay. There are really differences that are really strongly measured in the statistics. In fact, if we go on, we try to show some graphs. Okay. Perfect. So here we have parted the statistics for individual mathematical reasoning. So kids were given the test for solving a mathematical problem, and we can see that in 44 countries over 71, boys perform better in individual reasoning. And if we search for Italy, we see that if we search for Italy, we see that it is actually in the bottom. And so if we see that these bars are the difference between the points of boys and the points of girls. So here we say that from Romania going to the bottom, there are the countries in which boys perform better, while up there are the countries in which girls perform better. Mm-hmm. And we can see that almost every country that is near to us is in the bottom part. While in the right part, in the upper part, we see Finland, we see Norway, we see Sweden, just to mention some of them. Going on.
Sorry, where is France? I couldn't read.
Yes.
What?
France.
There.
Okay.
Here,
Okay.
a little bit, yeah, higher the average because this is the average.
Okay.
So a little above the average, but here in the part point outperform girls.
Sorry, what are the dots?
The dots are the standard variation of the behaviors. Yeah, in particular, we have the 10th percentile and the 90th.
And sorry, do you know what happens for younger boys and girls? There is an age where you start observing this difference in performance, or
Yeah, actually, we didn't find statistics for younger students. These, as I said, are done for 15 years old. So yeah, we are maybe advanced in education. I don't know.
I think already 6-year-olds. 6-year-olds at this point. Yes. Yes.
For you mean cultural?
Yeah. I think already a 6-year-old girl is.
Indeed, what was written in the report, trying to justify this behavior, was that girls suffer more from anxiety, math anxiety, they called it. Like when you gave a girl a test, she was really worried in the outcome of the test. And so she
which is mitigated if you work in a collaborative pattern.
Exactly. Indeed, if we go on in a collaborative problem solving, we see that in all countries and economies, girls perform better and outperform really the male performance. You can see here in this graph, the bars are the mean, so the mean difference in the points that they made, and the symbols are always the standard variation. In particular, here the problem solving is divided into a general scientific problem solving, a mathematical problem solving, or a reading one, so a sort of comprehension of the text that they were given. You can see that in the mathematical category, the standard deviation is what is more directed towards the male part. So there is more standard deviation towards the male part of the test, but the mean remains above the line. So in the region which we can say that girls perform better than boys in this way. The question is, why does it happen? They call it math anxiety, and they say that basically girls are more, I don't know if I would say influenced to think about the consequence of their failure in some kind of way. And we can see that also there is a difference between the countries. We saw before that Sweden and Norway, those regions suffer in a lower way this consequence, and we were very interested in understanding also your opinion, or maybe if you remember what you felt at this age, or if you encountered some little girls and can say that this statistic makes sense. Also living in Sweden, as you know, for one speaker.
Yeah, in Sweden, they say that math is a girl subject. And I mean, the popular feeling among, I don't know, teenagers is that mathematics is something for women. Then I think this is sort of true also in undergrads, but maybe not so much. Like in my group, we are 2 women in my area, so it's not like at the higher like researcher or a PhD level, then the situation is not very good, at least for what I can see from my department in Gothenburg. I don't know other universities in Sweden, but it is true that for this kind of age, they say that math is a girl's thing.
So, I have a question. Do you know if in this study they have also tested mixed teams. I guess like this is like the team made by only boys, and team made by.
No, actually, it was not with collaborative. We mean that a girl or a boy was in front of a computer with a personal assistant, and they could interact with this assistant. And so it was not groups of people. It was collaborative in the sense that they could interact. Exactly.
I was thinking that maybe one of the reason for both performing better in a collaborative context was they would share somehow success or failure instead of being 100% responsible. But that would not be the case if the collaborative means that. So
I think the collaboration somehow reduces the anxiety, and maybe they think, okay, the computer told me this, so basically I'm sharing the responsibility not with a person or with a computer, but maybe it works in a similar way. Like I have something concrete to address the choices that I made, not only myself.
Yeah, you can ask confirmation, like, am I doing this right?
I understood it correctly. Yes. Yes.
Sorry, can I ask you, this fact that in Sweden mathematics is something for women, can you, I don't know, quantify it in a sense, not quantify, but just say, is it among children, among teachers? Why do you think is it so? Is it because of the way of teaching math at let's say school level?
Yeah, I don't know. Yeah, maybe it's yeah, I think it may be the way that they teach in school. Also, I also think that they still have a lot the idea that people who graduate from mathematics will go to teach schools. So I think also in Italy this was the case a few years ago, that there were more women in maths because it was more popular to go to teaching in high school, while now there are a lot of careers like I don't know, software development, more company careers, and yeah. But yeah, I think in Sweden is more like the way that they teach in school, and I think this is something among high school kids that they have this, and also a lot of it's like the feeling of them. But yeah, I don't know.
Maybe also it is something that people can augment itself in the way, because there are more role models, and then maybe others has less problems in imagining herself being part of an environment that in which she can imagine herself. Otherwise, in other countries, it's more difficult, as maybe we said at the beginning, for the lack of role models or for the lack of narration of different kinds of participation in this kind of context. Maybe something like this, and that we understand. Okay. Now, the question that comes after this is, okay, how does this feeling of herself and the environment around her influence the choice that a girl out of the high school will choose, like a university path, or in particular a STEM path? So we talk about the percentage of young girls choosing university, and then young girls choosing STEM universities. First of all, we wanted to show the percentage of young girls and young boys who actually choose to pursue university. And we can see that throughout the years, they are quite stable, and in particular, we see that girls tend to choose more the university path than the boys. But going on, we want to ask you also in this kind of quiz that we made, which percentages, in your opinion, are the ones that actually involve in a STEM university, so in STEM future. Yes, both for the bachelor and for the master program. In Italy, actually. So,
in maths or all of them?
in all of them.
I don't have it.
No,
I would say
you
the
can, you can say
I would say the last one.
Yeah.
If you have
42 bachelor and 51 masters,
or first.
or 56 for
Anyway, high. Anyway.
high anyway.
Yes, I would say the first, because in mathematics, we have a good balance, I think, but for example, in physics, in computer science,
Engineering, there is the engineer. But there is biology as well. Could be that. Everything is mixed. And,
Have you got it? Okay, yeah. The right one was 36% in the bachelor, yeah, and 41% in the masters. And what we can say is pretty low, but it's increasing. One, as some of you said before, as Roberta said before, it is increasing once we go on with a career, university career. In particular, we can see that.
well, one should say also include how long does it take to get to graduation. I mean, one should put this variable in the study because, and then let's say compare female and male who graduate in the same time.
Because you feel that.
I feel that women
are faster.
would be better.
maybe with the grades.
Well, grades, I don't care, but time is
yeah.
Well, usually grade and time. If you grade in the right time, usually you grade, you have a good grade. If you graduate at the right time.
Yeah, actually, we can see that the percentage is quite stable. It is not.
But for math, it's pretty much 50-50.
We will see here. Oh my God. Here, you can see that they are differentiated.
Okay.
And it is, as we anticipated, biological and related science are the majority of them, and they are quite stable. On the other hand, physical sciences are more or less similar nowadays to mathematical and statistical sciences, and in particular, physics has been increasing through the years to 2013. Engineering is quite low, as we expected, maybe for interest reasons, maybe for cultural reasons.
Also, there are many corsi di laurea. I don't know. I mean, an engineer. There is. I mean, we have, for instance, in Tor Vergata, we have every year like 1,200 in all in distinguished different. So there are much more in mathematics. You have maybe one or maybe data science. So it's two.
Yeah, but they are still pretty low, actually, in engineering. Really, girls are not. I don't know. It could be for cultural reasons. Do we think that for some kind of attitude?
Yeah.
So, lack of role models.
Lack of role models.
Yeah, we don't even have a word in Italian for a female engineer.
And I think also social expectations. I mean, society expects women to do something and men to do something. Families sort of the expectations, I think, play a role. So in these choices.
Yeah, for sure. Going on in the master, the percentages are higher, as you can see, a little higher more closer to the average, to the 50-50, which means that in some way girls are more involved in the master's degree, while boys may choose to do something else after the bachelor. And showing also the statistics for the single STEM parts, we can see that engineering is higher, sure. So once a girl starts an engineer, usually she goes on. You can see that. Biological sciences are still at the top, while physics and mathematics exhibit somehow a change between what we saw in the bachelor case, because mathematics is higher. As you expected, you said that there was a 50-50 also in Italy. And do you think that actually the students who do a master in mathematics will end up being academic or do a PhD after that, or will teach in the majority of cases? Do you remember maybe being a master student, your thoughts about what to do next? Do you recall something?
I recall I never stopped thinking, am I right to do this job? As a student, as a postdoc, as a professor. This is my question. Well, I'm happy. I feel I am in my position, but I never stopped wondering this. But I think it stimulates me to overcome my limits. But concerning the fact that, do we think that after a master's degree, well, I would give a concrete example in my personal life. I am my oldest sister, who is 11 years older than me. She chose mathematics. She was an excellent student in high school, and she chose mathematics because it was at the time the study program with less exams. She succeeded eventually, and with the top level, and now she's quadro in generali. She never, I don't know why, but she never pursued academic career. She always worked first in banks, then in IT, then in insurance, and she became. And I always, for me, she was a big example. Also, she was a big example of the fact that as a mathematician, as a graduate, but then not graduate, as someone who studied mathematics becomes like can do basically whatever. Can become. We are I don't know the English term, ma siamo cellule differenziate. We have the potential to learn. I don't want to say we can learn any job, but we have the potential to learn. So this is very powerful to me, academic or not.
It's a trend that if you see in reality around you, for sure it makes a difference.
Physics as well, I would say. I mean, science is like mathematics or physics. I think I know many friends who are physics and physicists and do other jobs. I don't know any engineer who do a job different than an engineer or an academic.
Also, money is play a very important role in that.
Yes, I also like to say when supervising master's students, for example, writing their thesis and so on, I had in the recent past, different female students and male students. And I observed several times that maybe some male students were not, I would say, not top students, were willing to do the PhD after. They were convinced to try to do a PhD course after the master thesis. Whereas I had at least one case of a very good student, female student, who never thought about this. She had in mind something completely different. And I have a little impression that, I mean, it is more easy for a male student to be self-confident and maybe also to be some sense available to try to attempt to do something maybe without to be sure that it will success, but the idea to try is more natural maybe for a man than for a woman. I mean, this is in the impression just in the very little examples that I had the possibility to personally treat. So I think the educational and the cultural issue is really the key point in this type of issues.
It is also connected to the fear of failure that we call the mathematical anxiety 50 years old students. Maybe something that expresses itself in different ways, different times of the path whenever the person is called to take a choice, everything comes out and comes up. Okay, so maybe we will proceed on, going on to other stages in which I lead the word to Anna. So we continue to
Bella. So here we are, the PhD stage. So we will try to understand which is the percentage of female STEM PhD graduates, and we compare this with the all PhD graduates, so all fields, not only STEM. So now we'll ask you about STEM PhD graduates in Italy in 2019. So what is the percentage of female in STEM? Speakers, do you have any feeling about
the lowest?
The lowest. Okay, so you say 27.
There is still biology and chemistry.
Right. Yeah, you're right.
Maybe the 35.
I think also in I don't know any in biology or but I think also there the number of men who do PhDs much higher in percent.
I was speaking with a colleague from computer science some time ago, and she was saying me that in computer science they have very few students in the degree courses, but they have some PhD students because in that in that context where you can find some job outside academia which is more paid than the academic career, then male try to go there. No, so if some type of career is not the most paid, the most prestigious one, there is more place for women. So I'm doubtful about what it could be the answer.
So do you think this percentage is like closer to the one we saw for the bachelor or master degree, or maybe it's lower?
But even a field like I don't know, you will show the data, so I'm just guessing. But like humanities, like literature, I think the number of graduates, women graduates, are like, I mean, not graduate students, like master students, are like, I don't know, 80%, like a lot of women. But then in the PhD, they're like 50-50, more or less. So for this, not very hopeful.
Okay, so let's see the results. Okay, so actually the exact answer was 42%. So it aligned with more or less with what we saw for the master degree. Of course, it's STEM, so it includes all, not only mathematics. And if we look at the trend from bachelor to master to PhD, we saw this so-called reverse pipeline. So it means that basically, if you look at the variation of the percentage for female, you see that it's a little bit increasing between bachelor to master and then PhD. Becomes more or less, it stays more or less stable in PhD. If you look at the male percentage, it's reversed. So we start with a high percentage and then it goes lower in the master and remains more or less stable in PhD. So it is called reverse multiplied, and as I said, and this is in Italy in 2019. And yes, we see that basically maybe women are a little bit like more say, stimulated, yes, in like continuing the academic career, at least till PhD, then till while male maybe as also Veronica said before, they maybe tend to go not in academia but maybe in industry because they are more paid. Do you have any feeling about why it happened? And also, how do you think the percentages for all programs, so not only STEM, will be? I will show later, but how do you think they will be?
Yeah, I think that's about half and half.
Okay, so you think that it remains stable for all from bachelor to master to PhD?
I have no idea.
Because maybe we can say okay in like literature or other I don't know to say in English, in Italian we say umanistica, materie umanistiche, so other fields maybe there is more female presence that is maybe stable in PhD that can somehow balance this smaller percentage in STEM, or maybe not. Well, if we go to all, okay, all programs, the statistics are quite different, and we don't have anymore. We have still reversed patterns now, but it's completely different. So basically, you see that if you look at female percentage in bachelor and master in all programs, let's say that women go to university more than men. Okay, in bachelor and master we are at 56% more or less, and then there is a drop, okay, below 50% for PhD in all programs. While actually, if we come back to the STEM program, the female percentage is stable, so there isn't this drop anymore. So, if you want to comment about this, if you have any thoughts, why this happens?
But it's kind of balanced anyway. I mean, it's not far from 50.
No, it's not far
so...
from 50, of course. We are more or less there. And of course, I mean, there are these statistics include all the programs for one single year, more or less stable to years. So far. Yeah, it's quite difficult to comment.
Too many data confounded. Too many, yeah.
Oh, sorry.
Do you also data from mathematics, just mathematics?
No, for this stage, no. We had for mathematics for the master, bachelor, but not for the PhD. We will see some data for the SISSA. Actually, Professor Guetti spoiled that before, and she was really right. Really right in the percentage, but yeah, we will see first.
We can see also that in the PhD case, as far as we see, the female presence is higher than the average of other PhDs. Maybe because also the PhD in STEM is quite reusable in some kind of way. So there is a sort of practical thinking behind this choice. Maybe also you mentioned that in humanistic subjects, somehow the presence of female is higher during the bachelor or the master's, but then in the PhD it balances out, and maybe some male students proceed and female students do not. Also for expectations on the career, also for how they can rely on their future in these kind of research areas. Maybe with a STEM PhD, one can always say, okay, I can, in every way, I can go out of the academia whenever I want, and I'm not forced. In the other way, it feels like you are choosing too much, you're putting too much online.
Also, there's a lot more prestige, I think, in academic career in humanities. I mean, there's also in STEM, but in STEM there's a lot of other prestigious jobs, maybe in industry and in the private sector, while maybe in a lot of humanities there's less prestige in other kind of possibilities.
But it's very costly regarding the personal life.
And maybe it's even more costly because they have less money and so less positions, and it's much longer to become a professor. That's the impression.
Okay, so let's go to the final stage. So what happens after the PhD? We will show the percentage of female collected for Italy in 2022 in all the programs. So not STEM, but all programs for all the stages, basically, the academic career after PhD, so postdocs, permanent researchers. I think it was a figure that now there's more. Non-permanent researchers, so RTD, it is 2022 statistics, so it does not include RTT, so tenure track researchers, associate professors, full professors, and final directors. And then we see the same percentages actually collecting for all these stages for SISSA in 2023. So, okay, just looking very quickly at this plot, you can see there is a shifter, so it's called the shifter behavior indeed. And you see basically two different data. This one with points is for the year 2012, the one with bold line is for 2022. The pink lines are for female and the blue lines are for male. So in the x-axis you can see all the basically positions from students, enrolled students, so university, PhD, postdoc, and all the ones that I mentioned, arriving to directors. And you can see that basically, if we go back to the undergraduate, the percentage of female is higher than male, of course, considering all the programs. If you go to PhD, they are more or less balanced, but it's aligned with what we saw before. The percentage was more or less 50% before. If we go to postdoc, still balanced, and this shifter, okay, begins when we get to permanent and non-permanent retention positions. So basically here, you see that the percentages for male grow a lot, arriving at the 90% or less, and for the director position, we have less than 10% for women. Now we will comment this also later. I would like for now to go directly to the SISSA percentages, and then we will ask you later. So this is the last quiz for you. So actually, Professor Bueti spoiled a bit, so I hope you did not hear anything first. What are the percentages of female researchers from RTD on at SISSA in 2023? So
all scientific areas.
All scientific areas, yes. Neuroscience, physics, and mathematics. What do you think is the right answer?
Yes.
29.
35.
In mathematics, I don't see many women. Maybe.
Yeah, maybe remember that last year edition it was more a surprise for everyone. Now maybe I don't know, maybe because it's the second time we proposed it, maybe you already know. Okay. Okay, no, the correct answer, we don't have the correct answer. Yeah, okay. It's 16%. So it's
about the canteen. People are studying the canteen. This is what I saw at the canteen. Actually, I should have think about that.
The statistics from the audience are quite balanced, okay, between 16, 29, 23%. Dario was like always at the top. Okay, so here's the not the percentages, but actually the exact number of female and male. Female orange and male is green color from 2019 to 2023. So actually, you can see that the percentage is more or less stable through the years. Here we have a 16 over 99, number of 99, so more or less 16%. And it's dramatically low. So now we'll ask you why.
Sorry, can I ask you? So you show the numbers from 2019 on. Do you know something about, let's say, 10 years ago, 15 years ago?
Maybe
it was much worse, or maybe it was like that also?
I didn't find data, but these are easy to find. These are statistics found from MUL, so Minister of University. But actually, I found this data from 2019. They proposed me directly data. Okay. But I guess we can try.
It could have been better.
Yes.
In the past.
I had this impression.
Yes. Because SISSA was much smaller.
Yeah.
At least when I was a PhD student, maybe you were in 20.
Yeah, I graduated first 2003.
So let's say in the mathematics department, I think there were already Barbara and Tamara that stayed. Correct. This is
luckily at least
two numbers. But the mathematics department was much smaller. 2 out of maybe 18, 20. Now it's larger, and it has not increased in the mathematics department. But SISSA was not relatively small, much smaller, 20 years ago. So.
But now there are 3.
You're right. It's RTDA. Yes, I agree. Okay. Yeah, I mean, when I tend to think about permanent methods, and it's still in the mathematics department. And it has been two for decades. Nothing has changed.
But
So the problem is, from what Professor Rade said, that young people are not becoming permanent now, or are not like pursuing the academic career after PhD. Now, I guess maybe what I can say, maybe that also the economic condition of Italy in general, yes, Italy is changed a lot, and it's changing also through the years. Yes, it's evolving, and this can somehow influence people to say, okay, I will go to this. It's also what we, many especially students, are thinking in these years. So why do you think this phenomenon happens? So they call this phenomenon glass ceiling. So somehow women encounter obstacles. As I said, it can be economic, it can be family, it can be any obstacle that do not facilitate their advancement in the career. And so I would like to ask you why this can happen. So why may women be disturbed to continue the career, and why were encouraged, to continue your career in academia?
So more or less, we said all the reasons why there is this issue. We mentioned lack of role models because if you see very few minutes in the top level of the career, it's difficult for a young woman to imagine herself as a successful mathematician. But also, I think there are unconscious biases which influence self-confidence, and self-confidence is very important when you make some career choice. But also family expectations, society expectations, and so I think they are mainly educational and cultural reasons for it. And actually, I decided to pursue this career because I like this job very much. I like to do research. I like to teach, and as you can imagine, as you know, the most difficult period, the most doubtful period was between getting the PhD, completing the PhD, and getting a permanent position. Luckily for me, it lasted 2 years, so it's really not bad nowadays. But I think it is worth trying to do this because it is really a wonderful job. So I would encourage young women to try into this. And as we were saying before, mathematics give you also many other opportunities. So I think it is anyway worth to try if you like, of course, mathematics and like research.
I think one of the reasons why I think succeeding plays a big role, which is something that we don't, in the sense that I don't know, when you are the only woman in a room, and then it feels like maybe you don't belong there. And I have been the only woman in a conference. I have been there. I'm always the only woman in geometry seminars in my department. And so it's, I don't have a permanent job, so I don't know how long I will last, but I think that's, it is one of the reasons why we may say, okay, maybe I don't belong here. And then we know how it works when there's, so we said it in the beginning that men tend to be a lot more competitive and a lot less collaborative as an attitude, as a general attitude, of course, it's not like everyone, but there is a lot of this competitiveness that sort of runs in the group, at least in the group of people that I deal with. That's a bit hard to deal with. Then I was very lucky until now because I had two wonderful supervisors, and having good PhD supervisors make a lot of difference. Yeah.
I remember also last year, one of the speakers said, I do feel comfortable if I have a call with only males, and this is something that you say, okay, it's stupid, but it's not stupid because it's somehow related to math anxiety and what we said before. So if I have to rely only with males, maybe I can feel a bit less comfortable than in a mixed group.
Sure, I gave the data.
And the SISSA or
Yes, the SISSA.
okay.
I noticed something that I think is very interesting. It's the fact that so the permanent disability one is better than the non-permanent research, meaning that somehow the male can accept more risk. Maybe. And this is the beginning of then a situation that is amplified.
Mm-hmm.
If you put everything into what is the best job, what should be the other.
Yes. But I think that I don't know actually, but I feel that this is because this was a position, an old position, and somehow, as also Veronica said before, maybe before it was easier to get a permanent position, but it's my feeling.
So this is not for the same people. It's for the same people.
Yeah, if I review, so permanent position, permanent lecturer, then I don't know if now we still have these positions. Maybe I know that at OGS they have some, maybe at CNN they have some. They changed the name. They changed a lot, so. But,
also, I think that they
so
had.
It's not like
no.
The old time.
I guess non-permanent is both RTPA and then, yes.
But I don't really what I said is more of a historical problem.
Maybe yes.
I think this permanent researcher position didn't have much of a career possibility to advance the career. Like if you are at TDB, then you become associate, then full professor, and then. But I think the permanent researcher position was like it was a very good position, I think, but more like the same through life, and so much maybe easier for women to get one of these kind of less ambitious jobs.
Yeah.
Yeah, I feel like I have been very lucky because I always have been encouraged. I never felt discouraged in my career, starting here at SISSA, and my advisor were male. I never felt they would. I mean, people around me would behave differently because of my gender. But I think I've been lucky. Oh, the only rare few, maybe 2-3 times, I've felt uncomfortable as a female, where after I got my permanent position. So I'm grateful for that because I just felt a discomfort, which I just let it slide, and I must say they were because I was a mother and I was commuting, and someone told me, yes, but you are the mother. And it was so. This is one of. It was so stupid that it slid away. And I think that, yes, of course, it's not easy when you feel like you have been invited because you are a woman. Still, I do my job. I do it as best as I can. And even if I understand I have been invited only because I was a woman, okay, then, okay, I have to take the chance. And maybe I may not have the scientific level other men around me have. They may be better, but I'm here because I am a woman. Okay, I don't care. I try to do my best. And I feel okay with it. And maybe one of the things, this is a personal thing again, I was encouraged in this job is because my husband is as well, does the same job. So this also was like a proof of the fact that the ambient, the context is important. And
I have a little question about that. Do you think that if we aspire to a change in that, so if we aspire to have more females that are confident in what they do, it is more a question on, do we have to change our attitude in some kind of way, or do the environment, the external inputs that comes to us, help in some sense to change?
Of course, the system has to change. Yeah, I think so. I mean, I think what we saw in the beginning is this collaborative thing, which is one of the features of the sort of female education. So that little girls are encouraged to always have this collaborative and care kind of attitude, while little boys, children are always encouraged to be like more competitive and aggressive. Not aggressive, but like, yeah. And I think sometimes when we think about how to break this glass ceiling, we always think about women who tend to behave a little bit like men, who develop a more assertive personality, who develop a more competitive personality. And of course, there's a lot of women who are that and feel a bit trapped in the female femininity kind of thing. But I think progress goes towards embracing ways, in a sense. Very general.
I might be a bit provocative, but I'm just, I have no statistics. I'm not saying this as a statistic, just as my personal experience. I was lucky I didn't experience this glass ceiling. And in the sense, I didn't experience, I had obstacles in arriving at the best I could do up to today, let's say. And it's not finished, I'm 41, so I will do this job for many, many years. But I was talking to Antonio just before, who was a PhD student. He's 1 year younger than me. And so the provocative question is, are you the head of mathematics at SISSA today because you're a man and I am only associated professor at Tor Vergata because I am a woman? Or is it just because of our scientific, let's say, path and level? I mean, I don't think because this glass ceiling usually is associated also with the age. You compare not only how many women, but also you compare women and men at the same age, let's say, and you see that maybe that there is a gap even in this. Okay, but do I think this is gender related? No. In this particular example, this is not a statistic. I don't feel it is a gender gap. It's just the way it is. Yes.
But maybe if I can add that, because we're having this conversation. It is true that I never had this feeling that Annamaria was reporting of asking myself, do I belong to this community? And these little things, they didn't happen to your case.
Well, I just started saying that
yes,
I
right,
never quit asking myself
but
this question.
they certainly did not happen in my case. So I never had to confront myself with these things that could slow down and distract me when I'm doing research. You have to be focused, and this little thinking, like the buzz in your head, maybe this distracts you and you're not caught. This never happened. I have to be honest. And that's because I'm a man. And that's for me.
I don't think so. I think maybe, I mean, of course, the statistically men may be.
That's she was the only woman in the room. That certainly never happened.
Yeah, but
but related feelings that I think are totally. I mean, that don't get what I'm saying wrong. If in this room, maybe no one would think that Annamaria doesn't belong to this room, right? So these are not justified feelings. But if you look around, I guess you start thinking about this. This never happened. So just but not just in the career. When I work in the street, I never concerned can anything happen to me. And my wife is like, oh, but maybe I should not do that street late at night. And it's just type of feelings that I'm not used to. And if you add up all these things, men feel a little bit safer, comfortable. That's a fact.
Yeah, I think that's for me. I mean, of course, as she said, it's a question that everybody, I think, asks themselves often during their career. Am I doing the right thing? Am I doing the right choice? Am I right for this job? And you said it in asking yourself it a lot of times. But yeah, for me, it's a lot. Yeah, I remember when when I was a master student, we were a group of master students. We were not many people in the masters, so it was like we were a few girls and a few boys, and it was very normal. And almost all of my female friends went on doing a PhD. But then when I came for the PhD test here at SISSA, we were 2 women out of 40 people. And then I was the only woman in my year. And I remember one of my first days, one of my other friends in the office, first year students in the PhD students, asked me, isn't it weird for you that you're the only woman in an office of 8 people? And I felt like, yeah, it's weird. And it never stopped to be weird. And now I notice it a lot. And you are right. There are cases where I go to conferences and I feel like I've been invited just because I'm a woman, but then I've been invited to conferences where I was the only one, and I thought that was even more weird. And of course, then scientifically, I felt I fit sort of more because I knew that they had not been looking at like gender; they had been looking at who fits in this conference, and so I was there because there was a conference in my field and exactly with the people who do what I do. But then I also felt, I don't know, I was speaking at the conference and I thought about saying, guys, I'm the only woman in this room. But then I didn't say it. And I thought that was so obvious because when you are, but then I spoke about this with people and people said, oh, I didn't notice that because when you're privileged, you sort of don't notice these kind of things. And so, yeah, maybe I've been thinking of this in my life. But I have been, but that doesn't mean that I haven't been encouraged by a lot of men that I have met. But, yeah, but I feel like that's always weird.
Yes, it also happened to me several times to feel uncomfortable because, okay, there are very good women in conferences, but actually I didn't realize how this was uncomfortable until it happened to me to attend a school, the EWM school at Mittagletter. You know, EWM every year organizes a school for women in mathematics with the only request is that the attendance is half and half, so at least the half of the participants are women. And in that occasion, it was sometimes a surprise to find an environment which was quite different from usual environment in conferences. I mean, a more relaxed atmosphere, I actually felt more comfortable. So I really think that if we were able to construct a more inclusive mathematical community, this would be really great, because I think that it could be really a more stimulating community if there is more diversity.
Thank you very much for your interesting insight. Since we are a bit late, I would keep the very last question after the coffee break. So we do a second icebreaker after the coffee break, and then start with the talk. But it's very interesting. So we can, okay, what's this part? Yeah. We can go to coffee break at the ground. Okay, can I ask you to come here again just for 5 minutes? Okay, so we are back. Thank you for waiting. So I would like just to finish what we started before, and this is a website that you can find very easily. It's called Gender Equality Index, and basically here you can find different statistics for different countries, not only for women, wants, and basically you can ask the website, what does your life look like to the women from Italy, for example. And okay, if we go, it's not working. Okay, it was just me. Okay, if we look how this question is answered by the website, basically it gives very general statistics. So you can see the women from Italy, you are likely to live 4 years more than men. So, but what we are interested in are, for example, our representatives in the parliament that are 35% composed by women. And for example, related to what we also saw before, what is the chance of graduating from university for male and female? It is more or less the same, so 17–14%. And we can see, especially that at work, women earn 43% less than men, and that women are 38% percentage points more likely to go out of work than the men. So I mean, there are very dramatic data also in this case, and these are data for this year. If we try to ask the website, how does your life look like to the women from Sweden? I tried with Sweden because we have a speaker from Sweden. Things get much better. So it's not. It's not. It's a trend, of course, because in Europe we see that the statistics are dramatic, but they are less dramatic from some countries. So, for example, in Sweden, we see that women earn still less than men, but not 43%. We are around the 24% here. We are 15 percentage points more likely to do work, and in Italy we have 38%. The chance of graduating in university are higher. Actually, here both for women and for men. So it's, I would say, also cultural to the environment of northern countries, and also the decision makers in parliaments are includes much more women. So the final question I would like to ask the speaker is, how would you like the common image of a female mathematician to be in 10 years? And which aspects do you think should be valorized that now maybe are not? Start? If there are, maybe you can say, I think that the image should remain the same, which is also fun.
I think there's a lot of this idea in my field and with women that I interact with in my field, that there is this idea of women to be extraordinary in a sense. That you do something like super, I don't know. I feel like I've always had this idea that a man can be a normal professor, do their very good research, their good teaching, and have their nice personal life and be normal, while a woman to succeed in academia should always have something extraordinary going on. So I think my hope is that we can have more normal women, like average people who do their job and they're good at the job and just make it through this glass ceiling. But I don't know if that's the impression. You.
Yes, I have a similar impression from you. Yes, I wish that, I mean, women result with more recognized in academia, because sometimes I have the impression that, let's say, a result of medium importance, but which is presented in a very assertive way with a lot of self-confidence is more appreciated by the community than maybe a more deep result, but presented with humility, And so I would like that instead also, I mean, humility and a less aggressive way to present yourself could become normal. I mean, what I hope for the future.
Maybe I reverse the question. My answer is the reverse question, in a sense. I would like the image of a famous mathematician to be a common one. Right? So, but a common one, so there more, I wish there, I would like to, for there to be more women, only if they deserve it. I mean, my wish is that every woman, and every man, by the way, to be happy and to succeed in the job they want to do. Even if this means a gender gap. I mean, for me, the problem is not to get the same number, but to get the whole number of happy people, of not happy, let's say, of satisfied people with their job. So that would be my wish.
Okay, so thank you very much for your answers and for your presentation. So I guess that now we can start with the talks with the same speakers. So we will have Annamaria, then Veronica, and Roberta. Okay. Okay. So Annamaria will. Yes. Okay, just a moment. We can give also the slides into. Okay. Okay, just. Okay, would like just to see if.
I can also write on a tablet if you prefer, but I don't know.
Okay. Just to see if online is from online they can see the blackboard. Okay. Okay, so here maybe we can adjust. Maybe we can just
Sfociare solo questo, no? Vedo
Sì.
solo questo perché almeno
ok. Allora,
forse bisogna accendere uno di questi microfoni.
chiedo
Oppure no. Okay.
Okay, then the first speaker of today will be Annamaria Ortu from University of Gothenburg, and she will talk about scalar geometry and vibrations. So Annamaria, the stage is yours.
Okay, thank you. Yes, I will give a very brief and basic introduction to my field of research. A little bit what I do within this field, and so my field is scalar geometry, and a scalar manifold is an object. So it's a complex manifold. And where by complex I mean that for every there exists so locally around points it looks like Pn so is parameterized by over the complex numbers, and so equivalently a complex manifold has object which is called a complex structure, which is a map from an endomorphism of the tangent bundle, which squares to minus j identity, and so behaves a little bit like the imaginary identity. And also, scalar manifold also has Riemannian metric. Metric G. And so Riemannian metric is a way of measuring distances. On the manifold. And these two structures combine, so G and J combine in a composable way to form, which is so omega is a closed two-form, which is called an positive, which is called scalar metric. So we say that omega is called the scalar metric. And so the central question in my field is to central question. The central problem is when does admit a canonical metric. And a canonical metric is a preferred way of measuring distance on the object. And so canonical here means solution. So in the sense that it's a solution to a PD, to a partial differential equation that involves the curvature of the metric. So the curvature is a measure of the bending of the space. You can, it's a pretty intuitive also kind of notion. And so the central, so for example, the central example in my work is that of metric with constant scalar curvature. So they satisfy an equation of the form like this, and this is a complicated PD, it's a fourth order PD. So solving it from analytic methods directly is quite hard to do. But also maybe you may have heard of Taylor-Ritchie, Taylor-Einstein method. That can satisfy that the Ritchie method, the Ritchie curvature is proportional to the metric itself, and these are quite useful. And so, how does we produce our favorite metric? So, by the way, these PDEs that involve the curvature of metric are called we call them geometric PDEs when there is the curvature involved. And so one good feature of Taylor manifolds is that Taylor manifolds are algebraic. So for what I said until now, it seems that these are differential geometric objects, and we want to study equations on them. But actually, Taylor manifolds, or at least the ones that I'm interested in, are algebraic in which that they are subvarieties. So M is a subvariety of CPM. So projective, so compact. So projective variety. And okay, for example, when in the case of in the one-dimensional case, so in the case where M is a Riemann surface, then this question is always true. In the sense that so Riemann surface, it means that the dimension over the complex numbers of M is 1, so these are real two-dimensional objects. But so in this case, so they have been real dimension 2, these and compact surfaces. They have a genus, G, the genus of M. So there is this uniformization theorem. Which says that indeed M admits a metric with constant curvature. Which is positive in the genus 0 case, 0 in the genus 1 case, and negative in the genus bigger than 2 case, greater or equal than 2 case. But so in higher dimension, it's not true anymore that every manifold has a canonical metric with constant scalar curvature. It's not true that constant curvature metrics always exist. And in this, so this is why there is so this property of being algebraic comes into play because it is a general it is a general principle that drives most of the research in this field, that canonical metrics should correspond to algebraic stability condition. Yeah, so the stability conditions are involve the algebraic geometry of a Kerr manifold, and so they are defined in terms of some invariant, so positivity or some algebraic invariant. So in particular, for metrics, for these specific ones with constant curvature, the central conjecture of the field is the Young-Johnson conjecture. That says that the existence of a metric with constant curvature should be equivalent to an algebraic geometric notion called case stability. So these algebraic geometric stability conditions could be regarded as involving the symmetries of a space, while metrics involve more the differential geometric aspects of a space. So why are we interested in metrics or stability conditions? So this is because both metrics, so both the special metrics, canonical metrics, and stability conditions can be used to classify geometric spaces by constructing the moduli space. So a moduli space is space M, such that each point corresponds to stable manifolds. And also, it ideally should be itself a nice geometric space. So some sort of variety of complex spaces to have some nice structure. And so both these notions give a construction of a moduli space, a classification space. In fact, you can see from this theorem that classifying, so this theorem here for Riemann surfaces allows you to classify one-dimensional manifolds into those which have positive curvature, those which have zero curvature, and those which have negative curvature. And so we'd like to do a similar thing in a higher dimension, essentially. And so when one wants to construct this moduli space, there are essentially two steps. So there are two key aspects. So the first one is to understand the local classification. So understand how the geometry changes when so our starting manifold is deformed to M prime. So when we deform it slightly, so for small deformation. And the second key step is to understand behavior in families. So families are manifold connected. So a family is, for me, families of manifolds are these vibrations that are in the manifold and that are objects X to B, which are projections, where B is like the parameter space, and each fiber, so pi minus 1 of point, is a Kerr manifold. Research so far has been in either one of these two big themes, and most of it is kind of at the intersection of these two themes. And I don't know how much time I have left. 10 minutes. Oh. So maybe I can say something about something that I worked on last year. Which is sort of an example of these objects, which is the case of projective bundle. And so a projective bundle, if you have a vector bundle, is a family of vector spaces, and so we can projectivize it and consider the projective bundle, which is just taking the projective space of each one of these vector spaces that form the vector bundle. And this is an interesting. So if the vector bundle has rank R, then this is a projective space of dimensional -1, and so this it's yeah, perhaps it's the interesting thing is that apart from it being like quite a basic example of a vibration of this form that's kind of explicitly constructed, is that projective spaces are rigid, which means that they cannot be deformed. It means that the moduli space is just one point. So the classification problem for a projective space is quite trivial. But projective bundles are not. So when we consider families of projective spaces, then we have a lot of deformations. And so you see that this kind of problem becomes more rich for this kind of in this case. And just to end by stating something that I worked on last year. So together with my collaborator, Lars Martin Kleckner, also from the University of Gothenburg, we introduced a notion of stability on vector bundles called adiabatic slope stability. We use this notion to show that if we consider E vector bundle, so holomorphic vector bundle, and we consider the projectivization, and we assume that the base has a metric with constant curvature, then the total space, so P of E, seen as manifold X, has a metric with constant curvature if and only if E is stable in our sense. So this is something in the spirit of what I've been telling before about relating the existence of metrics with special curvature properties with some kind of algebraic stability condition. And the word adiabatic here means a limiting, so this is a limiting regime where we are sort of pushing the base B to become very large, so it tends to be flat in the limit, and the curvature is then concentrated in the fiber direction to leading order. So it's like a limiting behavior. And yeah, I guess that's all. Thank you.
Thank you for the interesting talk. Are there any questions, curiosities from people in presence here?
Yeah, sorry. Question is, when you talk about deformations, do you deform only the complex or the structure, or also the space itself? So
No.
that's the topology change.
No, topology doesn't change. Only the form, usually either the complex structure or fixing the metric, or the metric changes and fixing the complex structure. But surely the topology doesn't change.
Any other questions, curiosities, remarks from people online? No. So let's thank again Annamaria. And invite now Professor Veronica Felli.
From online, can you see the slides? I have to change the window that I'm sharing. Yes. Okay, now it should be okay. Perfect. If you want, you may use. La prima mi svede? Andando avanti si può. Okay. Okay. Then I will.
Okay. Okay. Then now I leave the word to Professor Veronica Felli from University of Milano Bicocca, and she will talk about Neumann eigenvalues in domain with more points. So Veronica.
Thank you very much. So in this talk I will speak about vector stability for the normal Laplacian in domain with points. So I will start with a general introduction on perturbed eigenvalue problems, and then I will focus on perturbations produced by removing small sets from the domain. First, considering the Dirichlet case, presenting what are the known results in the more classical case, and then I will focus on recent results on the normal problem. So, what is the question? We would like to understand how the spectrum of a differential operator is modified when you perform some modification of the domain, some slight modification of the domain. So the model problem I have in mind is the eigenvalue problem for the Laplacian, so minus Laplacian u equal to lambda u in a given domain omega, under some different kind of boundary conditions. You can consider the plane, Neumann, or even Boolean boundary conditions, and this is my unperturbed problem 0. Then I consider a perturbation. So the same operator with the same boundary condition, but on a different domain, omega epsilon. which is a perturbation of omega, and this epsilon is some small perturbation parameter. And then the question is the following: if omega epsilon is a small perturbation of omega, in a sense which of course must be understood, we would like to understand if the eigenvalues and eigenfunctions of P epsilon are close to those of P0. And if the answer is yes, then we also would like to quantify this closeness. So in the literature, first of all, you can find some results concerning the so-called regular perturbations. And I say that omega epsilon is the regular perturbation of omega if it is the image of omega through some diffeomorphism, pi epsilon, which is a C1 diffeomorphism with the property that the C1 norm of pi epsilon minus the identity map is small, so goes to 0 as the parameter goes to 0. And for example, in the book by Thor and Hilder, they consider this kind of perturbations, and they prove that in that case you have continuity, you have spectral stability for the Dirichlet problem, for the Neumann problem. So proving that the eigenvalues of P epsilon converge to the eigenvalue of P0 when the parameter goes to 0. But they also observe that this kind of problem is quite sensitive to the type of boundary conditions you are considering. Indeed, if you consider Dirichlet boundary conditions, so you prescribe the eigenfunction to be 0 on the boundary, then the result of continuous dependence also under the less restrictive assumption that the C0 norm of the deformation minus the identity goes to 0. This is true for the Dirichlet case, but it is not true for the Neumann case. Indeed, if you have homogeneous Neumann boundary conditions, the C0 condition would not be enough for convergence of eigenvalues, and they exhibit an easy counterexample showing this. So, also in the case of regular perturbations, boundary conditions play an important role concerning spectral stability. Now, what is instead a singular perturbation?
Sorry, may I ask a question?
Yes.
So, for the spectrum, what do you mean by continuity?
So I mean that okay, you have by spectral theorem that the spectrum is done by a sequence of eigenvalues. You enumerate these eigenvalues counting the multiplicity. So for each k, the k eigenvalue of the perturbed problem converges to the k eigenvalue of and also you have a convergence of projection on the eigenspace.
Sorry, and what about periodic boundary conditions?
What do you mean by periodic boundary condition?
The Laplacian of the torus.
The Laplacian on the torus, yes, on the manifold you should have the same type of result.
So no boundary, you say?
I think. Yes, and also in general manifolds without a boundary. Manifolds without boundaries, I think it should be. I don't know exactly what I imagine.
Yeah, this maybe your assumptions on
I still have to do that.
Okay.
I will be more precise in a moment because actually I will not consider this kind of perturbations, but I will consider singular perturbations. So a singular perturbation is just a perturbation which is not regular. And let me make some easy example. For example, you fix the domain omega, and then you excise a small hole from the domain K epsilon. And the perturbed domain, omega minus the hole, is a singular perturbation of omega because the two domains are not diffeomorphic because they are actually not even homomorphic. Another simple example, you can take a domain omega and you perturb by adding a small channel, a small tube with length fixed, for example, equal to 1 and a cross section which is shrinking to 0. This perturbation is a singular because if you take any possible deformation pi epsilon, you have that this is 0 norm of pi epsilon minus the identity is very small. Okay, but now from now on, I will focus on that kind of singular perturbation, so removing a small set from the domain. And let me start by telling you the story, what is known for the display setting for that kind of perturbation. So the first point is to understand what is the good notion of smallness, which ensures the spectral stability. But this actually was understood in an older paper by Rauch and Taylor in 1975. And they understood that this is related to the classical notion of capacity of the removed set. So this is the classical definition of condenser capacity. So you fix omega, which is bounded, connected, open. Take any compact subset K, and then the capacity of K in omega is given by the intimum of the energies squared of all functions in H10 which are equal to 1 on the set K. So by classical minimization tools, this intimum is achieved by the unique function dk, which is called the capacitor potential, and is the unique solution of this problem. So it is harmonic in the perforated domain, it is 0 on the external boundary, and it is 1 on the hole you have removed. Now, how this notion is related to that problem of spectral stability? Just by this easy remark, you have that the capacity of the set K is 0 if and only if the Sobolev space H10 of omega is equal to H10 of omega minus K. And this directly implies that the spectrum of the Dirichlet-Laplacian remains unchanged if you remove a set with 0 capacity. Just consider the minimax characterization of eigenvalues, since the fractional phases where we are taking the minimax remain the same, the levels, the minimax levels will be the same. And so the natural question is, what happens if I remove a set with small capacity? We should expect that the eigenvalues are closer to the eigenvalues of the original problem. So the idea is to use this capacity as a perturbation parameter to develop a perturbative theory. And this was done by Courtois on manifolds without boundary, and then by Bertrand and Courtois on manifolds with boundary, with Dirichlet on the external boundary. And actually, you have spectral stability because the validity of this inequality. So take any J, take the J eigenvalue in omega and the J eigenvalue on the perforated domain and consider the difference. Okay, the difference is trivially greater or equal than 0 because you have some monotonicity with respect to domain inclusion. This is true for the Dirichlet setting, but it's not true for the normal setting, as you can see. Okay, and so they proved that this variation is a big O of the square root of the capacity of the removed set, as this goes to 0. So this implies that if this is small, so if the capacity is small, then you have that the variation is small, so you have this continuity, this spectral stability. So is the reverse true? Actually, to have the reverse, you need to use a modified notion of capacity, which also involves eigenfunction. And this is the notion of phi capacity. So fix a function phi in H10, and then I define the phi capacity of K in omega in this way. I minimize the integral of gradient squared among functions in H10 which are equal to phi on the set K. In other words, f minus phi is in H10 of the perforated. Okay, also here you can prove that it is achieved, there is a potential and so on. And this quantity is the quantity which appears in the asymptotic expansion of the perturbed eigenvalue. This was proved by Courtois, and also we gave an alternative proof with Avatangelo and Elena. So fix a simple eigenvalue of the Dirichlet-Laplacian in omega, lambda n of omega. Actually, this can be done also for multiple eigenvalues, but for simplicity, let me just consider the simple case of the simple eigenvalue. Now, fix an associated eigenfunctions phi n to be normalized in L2, and consider a family of holes, K epsilon, concentrating to a set with zero capacity. Here there is the definition of concentration of set. I just mean that if you take any neighborhood U of K, then K epsilon is included in U for epsilon sufficiently small. Okay, so you have this family of sets concentrated to a set with zero capacity, and then we have this expansion. So the perturbed eigenvalue is equal to the limit eigenvalue plus the phi n capacity plus some remainder terms of higher order. And then in many situations, we can say what is the behavior of this quantity, which is actually asymptotic to the eigenvalue variation. For example, if K epsilon concentrates to a point which is outside the nodal domain of the limit eigenfunction, we have this behavior. So the capacity is asymptotic to phi n of x0 squared times the condenser capacity of K epsilon. In dimension 2, if the sets are concentrated to a point, this condenser capacity as a logarithmic behavior goes like 2 pi divided by the logarithm of the diameter of all. Instead, if you are on the nodal set of the limit eigenfunction, so phi n of x0 is equal to 0, some asymptotics can be derived in many examples. For example, if you have that those are these, or if they are segments. And in that case, actually, we find some polynomial behavior of the capacity, which is with the growth, which is related to the vanishing border era. And then there have been many related results. For example, for holes which are scaling, like epsilon times a given domain in dimension 2, or even in dimension greater or equal than 2. Okay, but now I would like to focus on the Neumann case. So the situation is the same. You fix the domain omega, open bounded connected Lipschitz in dimension greater or equal than 2, and consider the eigenvalue problem on the domain. Now let me consider instead of the Laplacian plus the identity map. In this case, the eigenvalues are just translated, so it's not restricted. So I have a family, a sequence of eigenvalues, lambda j of omega, and then I make my perturbation by excising a small hole. So I consider the same problem on omega epsilon, which is omega minus the closure of some set sigma epsilon. Now, what is the assumption on sigma epsilon? This is assumption H. I assume that, okay, these sigma epsilon are open, Lipschitz, the closure is included in omega. And then I need this property. The second property is a uniform extension property. That is, I assume that for any epsilon, there exists an extension operator between the two Sobolev spaces, H1 of the perforated domain into H1 of omega, with the property that the operator norma is controlled uniformly with respect to epsilon. So here I can put a constant which is independent of it. And of course, the holes are small. So the Lebesgue measure, sigma epsilon, is going to be. Okay, under this set of assumptions, Rauch and Taylor showed that you have a spectral stability. So the spectral stability is known under this kind of assumption. And then here I mentioned some results in the literature concerning spectral stability for this kind of problem. But now let me describe some recent results we obtained on this problem. So fix an index n greater or equal than 2, such that the anti-eigenvalue is simple. Something strange is happening?
This one of the
okay, I'm not doing that. No. Okay. But it's not disturbing. Now, please. No? Okay. Okay, why n greater or equal to? Because for n equal 1, the eigenvalues are 1 for both problems.
obtained by the constant eigenfunction. Okay, so there is nothing interesting to say for n equal 1. Okay, fix an eigenfunction which is normalizing N2. And then the problems are what is the asymptotic expansion of the variation? Can we say something about the sign of the variation? The sign of the variation is trivial in the Dirichlet case, but a priori is not known for the normal case. And what we found is that the analog of the role played by the capacity in the Dirichlet setting here is played by this notion of boundary torsional rigidity. So let me use the definition. So take a domain E, which is open Lipschitz with a closure inside of omega, and the function f in L2 of the boundary. Then the Sobolev F torsional rigidity of the boundary of E in the perforated domain is defined in this way. You take minus 2 the minimum of 1/2 the Sobolev norm squared on the perforated domain minus this boundary integral. Okay, this minimum is achieved by a unit function, capital U, which is a solution of this problem. So notice that you have homogeneous Neumann condition on the external boundary, and on the boundary of E, I am forcing the normal derivative of capital U to be equal to the datum F, which was appearing here. And then using the equation, you realize that this torsional rigidity is equal to the energies of capital U, so it is strictly positive, and also can be expressed as this boundary. And okay, this is a recent reference about the properties of this torsional rigidity. And let me remark that if you take a family of sets satisfying assumption H, you can easily verify that the torsional rigidity of the boundary of these holes relative to the normal derivative of the Lipschitz eigenfunction is going to 0. So this is a good perturbation parameter for our set. And this is actually what we proved. So recently, in collaboration with Liverani and Bene, we proved this theorem. So take a family of sets satisfying assumption H, so you have spectral stability. We also assume that the classical capacity of the holes is going to 0. And then we have this expansion for the eigenvalues. We know that the perturbed eigenvalues is equal to the limit eigenvalue minus the torsional rigidity minus this other term, which is the volume integral. So it is an integral on the whole sigma epsilon of this quantity, which just involves the limit eigenfunction. And then I have some higher order terms. Okay, can I say something more sharp, at least in some relevant examples? So to say something more precise, clearly the point is to understand what is the asymptotic behavior of these quantities here. And this, for example, can be done in some cases. For example, if you are in dimension n greater or equal than 3, we can consider the case of also scaling to a point. So fix the domain sigma, bounded open Lipschitz, and take as sigma epsilon x0 plus epsilon sigma. So you have this family of set which is shrinking to 0, keeping the same shape sigma. And also consider the associated perforated domain. We need it to be connected, so I cannot admit the case of annuli, for example. And okay, without loss of generality, I can assume that 0 equal to 0. Now, our general theorem applies to this situation. In particular, we have assumption H, so the uniform extension property is a property which is known. And also it is known that the capacity is going to 0 because we are concentrating to a point which has a 0 capacity in dimension greater than 2. Okay, so in this situation, our theorem applies. And moreover, in this situation, we can perform a blow-up analysis to understand what is the asymptotic behavior of the torsional rigidity. More precisely, consider K to be the vanishing order of phi n minus phi n of 0. Consider the torsion function u epsilon, and we scale it to consider epsilon to the power minus k u epsilon of epsilon n. We can prove that this converges to some non-trivial limit profile u tilde, which is actually a sort of limit torsion function because it is the unit minimizer of this problem. So this is a limit torsional rigidity of the boundary of sigma. So as before, you minimize 1/2 the energy, and in the boundary integral, you see here the normal derivative of a polynomial p, and this polynomial is nothing but the k homogeneous part of the Taylor polynomial of the limit eigenfunction at the concentration point. And then, using this blow-up result, we obtain this behavior for the torsional rigidity. We know that epsilon to that exponent, which is minus n minus 2k plus 2, so related to the vanishing order at 0, times the torsional rigidity goes to this limit torsional rigidity, which is strictly positive because it is exactly the energy of the limit profile with this value. And then, using this result, we finally end up with this theorem. So we observe different behaviors depending if the point at 0, where your all is centered, if it is in the singular set of phi n, or if it is not in the singular set. So if you are in the singular set, so phi n at x0 is 0 and also its variance is 0, that in that case we observe this behavior. So the perturbed eigenvalue is the limit eigenvalue minus epsilon at that power related to the vanishing order. And then I have this quantity in parentheses, plus higher order term. Instead, outside the singular set, we observe this other behavior. So minus epsilon to the power n, and here you have this long expression which involves the torsional rigidity and also the limit eigenfunction at the point. Now, what can I deduce from this theorem regarding the sign of the variation? So, in the singular set, you have a sign of the variation because the quantity in parentheses is strictly positive. In the other case, you don't have a sign because this quantity can be positive or negative. In particular, it is negative if you are close to a critical point of phi n, whereas it is positive if you are closer to a 0 phi n. And so, in that case, the sign depends on how you are located with respect to some limit interface gamma, which is the set of points where that quantity in the parentheses is equal to 0. Okay, so if you are exactly on gamma, you just know that the variation is the small o of epsilon to the power n. If you are instead outside gamma, it depends. If you are on omega plus, where the sign is negative, you have a sign for the variation. If you are on omega minus, where that quantity is positive, you have the other sign for the variation. So, particularly, if you are in omega plus, the perturbed eigenvalue is above the limit eigenvalue for epsilon small. If you are in omega minus, you have the reverse inequality. Okay, let me just conclude by saying that in the specific example of spherical holes, so for sigma being a ball, we have a quite explicit expression for this interface gamma, which is given by this formula here. And this actually holds true also for n equal 2, also it is obtained not by a blow-up analysis, but by direct computation making Fourier expansion. And then you can make also some specific examples. For example, what happens if you take a box omega and you remove some spherical also from omega? So if the size of the box have irrational ratios, then you know that all the eigenvalues are simple, they are known, the eigenfunctions are known, and this is the explicit formula for the interface gamma And then, for example, consider the first non-trivial eigenvalue, and in this picture you find the plot in blue of the interface gamma, which is just the union of planes. In green, the nodal set of the unique eigenfunction, which is the green plane. And so our theorem says that if you make the hole between the green plane and the blue one, the perturbed eigenvalue is below the limit 1, whereas if you make the hole beyond the blue planes, you have the other inequality. This is the picture for a higher eigenvalue. And finally, this is the picture for the disk. Also, in the case of the disk in 2 dimensions, you have many simple eigenvalues. And for these simple eigenvalues, you can find this expression for the interface gamma in terms of the Bessel functions. And so you can plot, for example, the interface gamma in some cases. So this is 2 pictures for 2 different eigenvalues. And so the theorem says that if you make the hole between a green cycle and a blue cycle, you have that the perturbed eigenvalue is below the limit 1, otherwise you have the reverse inequality. So I stop here and thank you very much for the attention.
Thank you for the very nice talk. Are there any questions from people in present?
So I have a question. So in these examples you showed, there is a way that is needed to compare L2 of one space with L2 of another space.
Sorry?
In all these examples,
yeah,
you have a way to compare the L2 space of one space, I'm sorry for the word space, or domain, and L2 of another domain, right?
Why? And what do you mean by L2?
The L2, the space of which you
space.
consider the considered equation.
Yeah.
And in this making the whole, this is a shrinking, as far as I understand. So in some sense, as a parameter of the perturbation, the L2 of larger parameter includes in the L2 of smaller parameter, and when the parameter goes to 0, eventually you will get the whole L2 of the domain. Is that correct?
Maybe I can understand your question. Why we say that you are not only comparing the L2, because actually you have the eigenvalues are related to quadratic forms on the H1, and I mean you have this uniform extension property, which allows you sometimes to compare also the H1. But I don't know exactly what you mean by.
I just wanted to say there is a so because these equations are formulated from different spaces.
Yeah.
And you need to, when you say that something is a smaller perturbation of something else, in this case of the spectrum, it's clear. The given functions, what does it mean? So you need a way to compare it. In some sense, you are exploiting, I guess, the fact that these domains are subset of the original domains. The third are a subset.
But in some sense, but yes, in some sense, yes, but
my question is,
yes.
I was wondering if there is a weaker notion, like a family of spaces that depends on some parameter in some topology, not clear what it should be, and this guarantees stabilities of family of the eigenvalues of the family of some of the.
Yes, maybe your answer in a more general abstract setting, so consider eigenvalue problems for quadratic forms defined.
Because the theory of perturbation of the ability of it is clear.
Same
domain, but the perturbation operator.
Yeah.
Can one make this?
You can mean things by thinking of perturbation of the spaces and of the quadratic forms, let's say. There is some result.
In a family.
Yeah.
Like this is.
Family depending on the parameter.
But this is what is happening somehow.
Yeah.
This family converges. I don't know. clearly in Hausdorff topology, but maybe in some other topology that guarantees that there is stability. That's my question. Maybe it's super obvious.
I should think a little bit about it, but yes, I think that in some sense something that is done in this direction.
Okay. Any other questions here? Presence?
Sorry, you have a way to do something about the perturb eigenvectors.
Yes, about the eigenfunction. Yes,
They might be a mess, no?
Sorry?
They might be very different from the other.
The eigenfunctions, we
Yes.
For the eigenfunctions, we can say something. We can, okay, of course, for simple eigenvalues. First of all, we can make some blow up for eigenfunctions. So, result of the type. If you make a scaling of the eigenfunctions with some order related to the order I found in this function there, they go to some profile which can be recognized. So, but also we have an estimate of the H1 norm of the difference between the perturbed eigenfunction and the limit one. This also can be done, at least for n greater or equal than 3. So in the case of simple eigenvalues, you have some convergence of the perturbed eigenfunction to the limit eigenfunction, and you can quantify in an energy sense the order of this convergence. So they are close to the limit eigenfunction.
So due to time, thank you again, speaker. First and speaker.
Lo faccio.
The first and last speaker today is Professor Roberta Ghezzi from University of Roma Tor Vergata. And she will talk about regularity of unbalanced optimal.
Okay. Thanks again to Isabella and Carla for the invitation to give this talk. And I will talk to you about this work, which is a collaboration with Thomas Galouet from Henriat Saclay, François Xavier Vialard from Gustave Eiffel Paris. Okay, so the first part of my talk, I will be introducing briefly what are the formulation of classical optimal transport in Euclidean and Riemannian setting, and then generalized to the unbalanced case. And the second part will be concerned with regularity, where by regularity I mean once I have a solution, what can I say if I start from initial smooth data, what can I infer about the regularity of the solutions. And I will give the basic ideas of our work of how to deduce regularity of unbalanced optimal transport from that of classical optimal transport. And I will introduce the objects of interest, which are the Max-Rodinger-Wong tensor. Okay, so this is the reference. No, sono andato indietro. Okay, so the optimal transportation problem, I think it's finished. Well, it is well known. I don't know in the audience what are your expertise. But so the idea is I take two probability measures. So let's say in the Euclidean space Rn, and they represent some mass distribution. And I have a cost function, which is a positive cost. and it represents the cost to transport a unit of mass from position X to position Y. And the main question is it possible to transport the whole distribution mu to the whole distribution nu, minimizing the running cost, which is given by this integral. So the integral over the whole space of the cost of transporting a unit mass from X to T of X, where T is the so-called transport map, so which maps the measure mu, it pushes forward it to the measure nu. And the typical, so the first examples where this cost is a cost of expressed in terms of distance, so Euclidean distance for distance squared. So okay, one of the first results is due to Grenier in the late 80s, and he proves that if the two measures are compactly supported and the source measure is absolutely continuous with respect to the bag, for the cost given by the square distance, there is a unique solution to the Monge problem I stated before, and moreover, the optimal transport map satisfies this, can be represented as the gradient of a function p, which is convex. Moreover, if also the target measure is absolutely continuous with respect to the bag, then we have this Jacobian equation, so on the determinant of the gradient of t, where here we have the relation between the density of the source measure and the density of the target measure at the transported point. And the value function of this Monge problem, so the infinium, is what it is now known as, the Wasserstein distance between the two measures. Okay, so this was generalized. It took quite some years. This was generalized to in different directions. One is the direction of the space. So here we are talking about the Riemannian manifold, and the other one was in so of course, and then results for different costs than the distance. So this is the theorem by Bekan, who proves that if I have two probability measures on my Riemannian manifold and a cost which is which satisfies the so-called twist condition, meaning that the first so the gradient with respect to the first group so the first point is injective. If the source measure is absolutely continuous with respect to the Riemannian volume, which is the analogous of the bag measure for Riemannian manifold, then the Monge problem has a solution, which is again represented as by the gradient of a C convex function, where convexity so here involves the cost C. And there is this C exponential, which is the identity in the Euclidean case, and here it is linked to the cost by this equation. So the C exponential of a vector v is a point y if and only if minus gradient of the cost function at point xy is equal to b. So this is why we need this inductivity. And again, there is a Jacobian equation if both if also the target measure is absolutely continuous.
So can I ask you a question? A quick question. I mean, when you say that this map is injective, what do you mean that? Because
as a map of y.
But so that's distance. For every fixed x, you consider the gradient at that x, and you let y change.
You put a C dot here, yeah.
Okay.
As a map of y. Okay.
At every fixed tangent space. At every fixed tangent space.
Yes. So this is in order for this to work out as a public implication, right? Ok. Oh, niente, per me andare avanti è nessuno. Sorry. And in the same years, there was an important contribution in the setting of optimal transport, which was to give a dynamical interpretation of the Wasserstein distance. So basically, Benabou and Bernier, they proved this, that the Wasserstein distance, which is defined in these ways as the solution, the infinium of the Monge problem, can be obtained as well by this infinium procedure, where this holds true for measures which are absolutely continuous with respect, both are absolutely continuous with respect to the Riemannian volume, and the problem is to minimize this cost. So where we take the infinium of the integral between 0 and 1 and the integral over m of what this is a kinetic energy, norm of v square, where the norm is given by the Riemannian structure, and the pair rho v is a pair that satisfies this continuity equation. So basically, we consider densities of measure which are time independent and space dependent. And with respect to the time variable, we ask that this condition holds true, meaning that we do not create nor destruct any mass. And the first, the initial condition at time 0 should be the density of the source measure, and the final one should be the density of the target measure. Okay, so from this formulation, it is quite natural to ask what happens if instead of a continuity equation, I put here a source term. And this is what it is called, now called the unbalanced optimal transport problem, which amounts to generalized optimal transport from measures with total mass 1, or let's say measures with the same total mass, to measures which may have any finite and positive total mass. So I relax the constraint to have the same total mass. So passing from probability measures to positive random measures. And one possible way of defining this this problem is to consider on a Riemannian manifold, to consider two positive random measures and consider the infinium of. So this is the same functional as before. There is a kinetic energy plus a potential energy, and the constraint would be this partial differential equation here, where here we have a linear source term, linear in the density rho. Okay, and so so this was the subject of research of different groups in the same years. With contribution, for example, for different terms in this work, there is a more generalized term of source, not only linear. Whereas I would say that these three groups, research groups, work in the similar context, but they are driven by different questions. These were more driven by the SISSA, etc., and the Monsanto, etc. They were driven by more numerical questions, whereas the group with Giuseppe Savare, they developed a theory. They cast the unbalanced optimal transport problem in a theory of entropy transport problems. So, and one of the contribution in this work here is the following: is that this is sorry, I didn't mention WFR means Wasserstein-Fischer-Rao distance. defined in a dynamical way, as I did in the slide above, admits a Kantorovich formulation in this way. So here, what do I have? This is the cost as the classical cost in optimal transport for some function C, but I do not minimize only this cost. I also minimize these two objects here, which are, so this means that the marginals of my optimal transport plan, they are not required to be equal to the source and target measures, but we only ask to minimize this entropy, where this entropy is formulated in terms of the two measures in this way. It is a logarithm type of entropy. And the cost that appears here as an explicit definition, it is this one, minus logarithm of cosine square of the distance, the maximum between the distance, the minimum between the distance between 2 points and pi over 2. So with respect to classical transport, I have this term here, and I have a cost which may blow up, right, when the points are at some distance pi over 2. So, and these works were concerned with results of the type the dynamical formulation is equivalent to this formulation, and also of existence of solutions. Okay. Among the formulation they give, there is also a dual formulation, which is this one. So the infinium over the of this problem here, which is expressed in terms of plans. So these are random measures on the product n over n. It can be, it admits a dual formulation in this way, where here we take the supremum of the sum of these two integrals with respect to pairs of continuous functions. So bounded if we are on Rn, on the compact manifold, take bounded functions. And the two functions should satisfy the constraint that the sum should be less than or equal to the cost function. So starting from this formulation, and from the fact that the unbalanced case is not far, let's say, so the point is here is the following, that these these minimizations here are independent from each other. So somehow, once I minimize these two objects, I can say that the marginal of gamma are fixed, and somehow I can solve a classical optimal transport problem between fixed marginals, which will not be these two, it will be different, but will be fixed. So once the problem is considered as a classical optimal transport, I can apply the machinery of regularity for classical optimal transport problems. So, and this is the idea of our first result, which can be roughly explained in this way. So, under some admissibility conditions of the two source and target measure, I will say a word about this admissible in the next slides. So, if the classical standard optimal transport problem with this cost enjoys regularity, what I mean by enjoys regularity, I mean that starting from, let's say, starting from CK alpha regularity of densities of the measure, I gain C2 regularities of the potentials, of the optimal potential. And if I can start from optimal potential in the dual formulation, which are at least Lipschitz continuous, then I can say that the regularity of the optimal transport implies a regularity of unbalanced optimal transport. So this, the rest of the work is based on how to find the sufficient conditions for this cost to enjoy regularity property in the classical sense, and the existence of Lipschitz optimal potentials for the dual formulation. So, and what we found is the following. So let's say before, so as concerns sufficient condition for regularity of optimal transport, the theory of regularity is now well understood, and one of the ideas is based on the following fact. So this here I am in classical optimal transport. Assume I have my solution, which is given as the C exponential of the gradient of a complex function, and it satisfies this equation. So if you differentiate, so somehow regularity of T is related to regularity of solutions of this equation. So differentiated twice this equation, we get a linear PD in second order equation of psi. So where psi, I recall, is the convex function whose gradient appears in the definition of the transport map T. And so somehow, this is what is called the Monge-Ampère type equation. And the regularity of solutions of this equation is related to some a priori estimate, which needs the quantity, some quantity to have a definite sign, and the quantity is what is now called the Max-Rundinger-Wong tensor, which is this object here. It is an object involving derivative of order 4 of the cost, computed along curves that start at different tangent vectors at the point x. So, so this is what Max, Rundinger, and Wong proved. They proved that if this tensor is satisfy a positivity condition of this kind, so it can be bounded below by a positive constant time the norm of the two vectors, whenever the two vectors are orthogonal, then starting by smooth densities allows to prove that the transport map is smooth enough. Of course, apart from this, let's say, direct hypothesis to be checked, there are some other conditions that we need. Of course, well, the cost should be regular enough, because here we have derivative of order 4. There should be the twist condition in both variables, some non-singularity of these second derivatives, and also there is a condition between the supports of the source and target measure. This is a condition that allows to prevent some topological obstruction for a solution to the regular. And then this positivity condition of the tensor is sufficient. Once all these conditions are granted, this implies regularity. So for our unbalanced case, we computed explicitly the tensor associated with this cost function. And of course, so the idea we did, we have two strategies. First one, which I call direct strategy, which amounts to compute explicitly this tensor. And this can be done on spheres or in the Euclidean space, because here we know geodesics, so we know how to compute the distance explicitly between 2 points. And what we proved is that the Max-Rundinger-Wong tensor does not satisfy the positivity in the Euclidean case, and it does not, so the condition fails also on spheres of big radius, or radius bigger than 1, whereas the condition holds true for radius 1 and 1/2. So what we prove is that the also solutions to unbalanced optimal transport on the spheres are regular in this, at least in these two cases. Of course, one would ask, okay, what for other radii? Well, we weren't able to prove the condition explicitly for the other radii, but we conjecture that indeed it should also hold for all radii between 0 and 1. And as concerned the existence of Lipschitz, how much? Finished? Okay, 2 minutes. As concerned the existence of Lipschitz potential, there is this contribution by Galouette and Vialard to prove that if the two measures are admissible, what does it mean admissible? It means that somehow, so this is a condition that prevents the cost to blow up at points of the two in the supports of the measure. So this condition here is somehow the meaning is that the two measures should not see charge points at which the cost is infinite. And under this condition, there exists a unique, so that there exists a Lipschitz continuous optimal potential, and it's this is the unique solution of the unbalanced optimal transfer, and it satisfies this Monge-Ampere equation. Maybe just I go to the last fact, which is the following. There is also, so once this optimal potential of Lipschitz continuous exists, we can prove that the Wasserstein-Fischer distance admits a Monge formulation, where the Monge formulation this time it is not on the manifold, but over the cone. So where the cone is n times 0 plus infinity, you can interpret this cone as the set of Dirac masses pointed at x with the density r, with total mass r. And so this is the Monge formulation, where this distance is the Riemannian distance on the cone, which is the Riemannian distance on n multiplied by R2 plus this Euclidean distance on the outline. And this formulation allows us to interpret also the regularity, the questions of regularity in a synthetic way. Why in a synthetic way? Because we prove that the Max-Schrödinger condition for the distance square on the cone implies the Max-Schrödinger condition for the cost, the unbalanced cost on the manifold. So this provides a way, if we do not know how to compute geodesics, so for many general manifolds of different from the spheres where there is some explicit way of describing things, we can say that if the condition holds up on the cone, then the condition for the distance, the condition should also hold true for the cost on the. So maybe I just leave the last slide, which contains some open questions. So one question is, can we say the vice versa? So are they equivalent? MTW condition on the manifold for minus logarithm and the MTW for the distance squared on the cone. It is not clear because, of course, the projection from the cone to the manifold introduces singularities. This is the conjecture on the spheres I mentioned before. And then an interesting question is, are these results stable in a way? What happens if I perturb the Riemannian structure on M? What can I say about regularity of bounds? Thank you for your attention. Sorry for going further.
Any questions?
This is like where you find the dynamical formulation of this document. The alpha is there. Is it depending on both space and time? Is it constantly something?
No, just on space.
Just in space.
Well, no, I'm sorry. No, this is both time and space.
Okay, so this does not extend the definition of what we call the sustained distance, but in general, it's less, right? Even between measures with the same mass, right? Or am I wrong?
Okay. So if I take a measure with the same mass, this is when alpha is equal to 0, you get classical. If alpha is different from 0, what is the relation between the two? Is there an inequality? I don't think we get an equality for everyone. For every pair of measure. Yeah, but the equation is different. Yeah.
Well,
Yeah, but imagine you're adding alpha squared.
yeah, but if you take alpha equals to 0, you get the same addition over the others, which should be good. So this should be less.
If alpha is equal to 0, yes.
Yeah, the point was that this is not extending, right? The usual definition. In general, it can be strictly less than the usual one, right? You have.
Yes, generally it is
different.
different.
Okay. And is there any relationship between this formulation of unbalanced transport and the Ellinger approach distance?
Yes, we're talking, the versatile is the same. Versatile Fischer-Rao and Ellinger control, which is the same. Yes.
Okay.
Yes, it's the same. We're talking about the same thing. Yes.
Is it very true that, if the two have the same mass, you can get something different from the versatile distance?
I mean, you can.
But if you introduce this term here, this alpha is a given.
No, it's the infimum over all the alpha, rho, the alpha of this quantity,
yes.
as it is.
Yes.
So, the infimum over rho, the alpha.
Yeah, but it seems that in some cases it's convenient to make some masses appear from some place and make it appear in another place without actually including.
You're right. Yes, I agree.
Yeah, because
if you have something, it's better to go straight instead of moving.
Yeah, just correlation with the common correlation that they are.
You allow for local changes of mass even between measures with the same total mass. You allow for.
Oh yeah, it's like when you're on a cone, no? Unless you look at the polar coordinates on the sphere. It is more convenient if you are in some regime to go straight instead of moving on the sphere. Yeah, okay. Yeah. It's like a space which is a cone. The mass is the extra variable.
Yes. That's the end of the. It has a conical formulation. You can even interpret these elements in the cone as Dirac masses. There is a recent work by Giuseppe Savare and Giacomo Enrico Soldini, who they prove that actually this admits not only in the general framework of entropy transport problems, but also in a much more general context. You can see this unbalanced optimal transport as a relaxation of a functional over Dirac masses. So since Dirac masses represent this cone, yes.
Yeah, I have a much simpler picture in mind, but yes.
Yeah, because of.
Any other questions? Any questions from people online? Yes. No? Okay, so let's thank again our
Thank you.
Thank all the speakers of today. this edition of SISSA Women in Mathematics. We were very happy to have you here at SISSA. I hope that also the audience liked this edition. If you have any suggestion, any comment, positive or negative, you can send an email to me or Isabella, and we or other people next year will try to address. So thank you also to the audience and Professor Lerario for being here in the end. And